Hello everyone. So today we will be looking at a vibrating string, which is a PDE, and this was the info given to us. So they gave us the mass density. Um, they gave us those boundary conditions, the initial conditions, and also note that the K in the one boundary condition, so this one here, the K is the spring constant in Hooke's law, and then T is the tension, which is the initial tension. We're assuming small um, uh, perturbations, so the tension can be considered to be equal to the initial tension. Now, the question asked us to solve the differential, but they said that we can assume that the eigenvalues and the appropriate eigenvalues and eigenfunctions are known. So we don't have to solve them. We know they are there and we know that they are appropriate. Then they asked us to what differential equation and what boundary conditions will our eigenfunction satisfy, and then to what weighting function will our eigenfunctions be orthogonal. So to do that, let's start off with maybe writing down the standard, the partial different, the PDE for strings. So you can check this in any text that deals with partial derivatives, but it comes down to this. And note that this part is actually the gravity, it's the body, the vertical body forces, and it's very negligible relative to the other forces. So we're going to neglect it. So we can actually dumb down the partial derivative to something a little bit simpler. And then just to point out that c squared, if you check the derivative or the derivation of the PDE for a string, you'll find that this is actually your c squared. So the way to solve this, they said we can assume that the eigenfunctions are known, but let's first maybe separate the equation into its two dependent variable by assuming a product solution like this. If we substitute that, we will end up with this. We'll end up with this. Sorry, this is supposed to be the t part, not mistake. Okay, so now we can multiply both sides by this. Okay, and then I'll end up, as I'll have, I'll end up with this. Okay. Now I have two sides, left and right, and the one is dependent on t and the other side is dependent on x, and yet they are equal. So it's two functions dependent on different independent variables, but they are equal. So they must be equal to some constant then. And we'll go with the conventional, which is minus lambda. So I'll end up with this. I'll end up with this. And then my other one, which is c squared. But hold on, let's because we know c squared is that other constant, so we can write it out like this. Okay. Right. So this is my two functions, and actually this one here is my eigenvalue problem because it has two boundary conditions. Remember correctly. The one is at x equals 0, sorry. So and we set the movement there is 0. And then the other one is actually the derivative at x equals L, that was equal to this. Okay, and now we've actually given the answer of the one request, which was what differential and what boundary conditions will be satisfied by my eigenfunctions, and that is actually the one that's my eigenvalue problem. So I know that I've answered that question. The other one, we have to solve this, but before we can really solve it, we need to have a little bit more info on lambda. So we know that if lambda is equal to some positive constant, then we will have oscillating solutions because we've chosen minus lambda as the separating constant. If I were to substitute lambda as a negative constant, then I'll end up with exponential solutions. Now, intuitively, one knows that I don't want exponential solutions here because it's a vibrating string. So over time, I'm expecting to view oscillations and not exponential decay. So because there's no resistive forces, we've neglected them. So I'm assuming oscillations. But we can formally investigate it. So meaning intuitively, I know that lambda should be positive. But there's also a more explicit way to show this, and this is through the Rayleigh quotient. So the Rayleigh quotient, we can actually go back to the spatial part, which was this. We will substitute it with a normal, we'll change it to a normal derivative since this function is only a function of x, so it's not a partial derivative. We will then have this equals to 0. Now, if I multiply both sides by my function and I integrate by x, I'll end up with this. Okay? Plus lambda from 0 to L. Okay. Now, if I want to solve for lambda, I'll end up with this. So let's solve for lambda. Lambda equals going to be minus t integrated over the range. I have second derivative in terms of x, and this with the dx here. Okay. Then I have this. So if we look at the denominator, so this part is positive. We have a mass function, mass density function, which is positive. We don't have negative density anywhere. So we have positive density, and then we have a squared function, and the integral of that will be positive. So it's easy to see that we have a positive function here. What we do want to investigate is we want to see, so we're not going to calculate lambda explicitly. We rather want to determine whether it's positive or negative. And if we go for if we look at the numerator part, we can do integration by parts. And if we do this integration by parts, we'll end up with something as follows. So we'll have, this is going to integrate over the range, and then we'll have plus, this is going to be, this is not the second derivative because we've integrated, excuse me. Okay, squared dx. Right, so let me just scroll to the right so you can see. So that is the integration by parts. So my lambda, meaning my lambda will be equals to minus t. And then if we investigate, let's maybe investigate this first part. So we have the boundary conditions for these two. For both these functions that are being multiplied, we have the boundary conditions. So if we substitute our boundary conditions at L, we'll get this. We'll get this at L. It's minus k t. Then we'll have squared. Okay, the square in the right place. Squared. The other one, so at the boundary 0, the terms will become 0 since we know there are no movement there. So it's fixed. So that part becomes 0. We only substituted the L part, which is that. And then we have plus T0. And this part, This part will be positive since it's the integral of a squared function. So we're expecting it to be positive. We've already shown that the denominator is in fact positive. So now if I multiply the t inside the brackets there, then I'll end up with this. Okay. And which is great now is based on the terms that make up lambda, even though we haven't calculated lambda explicitly, the terms that make up lambda is all positive. Since we have the product of the spring constant in Hooke's law, which is positive, with a squared function or squared value, which is also positive. This is the integral of a squared function, and this one we've already said is positive. So I can safely say, thus, lambda will be greater than 0. And intuitively, we've shown the same thing, right? So if I go back to my derivative in terms of t, I can now solve this. Since I know lambda is positive and I've chosen the minus lambda, we're expecting, so now we know that t will be a superposition of the oscillating functions we have. So we have cos and sin, right? And we're going to superimpose them. Since we don't want to leave out, I'm not going to say it's just the one or the other. We're going to say it's a superposition of the different oscillating functions, which is now cos and sin. And also we have a very convenient, I'm going to take the derivative in terms of t. Here I'll end up with minus c1 square root lambda sine square root lambda t plus c2 square root lambda cos. So I'm taking the derivative because remember one of the initial conditions that was given to me was the fact that it's fixed, so there's no movement there at the start. So if I substitute t equals 0 here, if I substitute t equals 0 here, I'll end up with my one condition, which was it's 0 there. And then when I substitute 0, this becomes 1, and this one will disappear. So I'll end up with c square root lambda, which is equals to 0. We know that lambda will not be 0, so thus c2 must be 0. So my function in terms of t is very simply then just a cos function. Okay. Now that means, also remember that I have infinitely many eigenvalues and eigenfunctions. So actually my solution is the product of the spatial part times the one independent of t, but we must superimpose over all eigenvalues. So this is going to be an infinite sum over all eigenvalues, where n will start at 0. We have coefficients, we'll have our eigenfunctions, and this is just the product solution that we got at the top. I'll remind you now. So remember we said that the solution at the top we said is actually a product solution of a spatial part and t dependency. Just scroll a bit to the right so you can see. That is what we said at the top. But since we've shown that we have an eigenvalue problem and we have infinitely many, we have to take the superposition of all eigenvalues. And it's the product of an eigenfunction times the function in t with its respective eigenvalue. Okay. Next, I can use the initial condition to solve the coefficient. But before I do that, I will need to take the Fourier transform on both sides. But before I can do that, I will need to then know to respect to what weighting function will my orthogonal functions be, will my eigenfunctions be orthogonal. The way to do this is we're going to go back to the spatial part, but we're going to use two different eigenfunctions. Since we have infinitely many, we can use any two. We'll choose them at random, doesn't matter. So then I'll have this. we will substitute it again with a normal derivative, which was this. This is also n density. And then we'll use another one, which we'll use a subscript k. That's not nice. Way you get the idea. Subscript k. Okay, if I multiply this side by this one eigenvalue, and I multiply this one by this eigenvalue, and I subtract the two equations, I'll get to this. So I'll end up with T0 divided by this one minus 0. Then k subscript n. And then we'll end up with, let's say, minus lambda n minus lambda k. And the product of the two different eigenfunctions. Okay, eigenfunctions. Now I'm going to multiply by minus on both sides just to get rid of the minus on that side. So we'll end up with first minus T0 okay, now we just got rid of the unnecessary minus. Now I want to point your attention to these two functions on the left. So I can actually substitute them with the following. If you remember correctly, if I have a derivative like this, so I have, remember correctly, I have a second derivative of my k1 times my n1, and I can actually substitute it with this. Will be minus, then I have to subtract this. I will have to subtract okay, the apostrophe is an indication of the first derivative. And you'll check that because if I apply this derivative, to the one in brackets, I have to use the chain rule, and the chain rule will end up with a second derivative in the eigenfunction k times the eigenfunction of n, plus we'll have then the first derivative in the eigenfunction k times the first derivative in eigenfunction n. So I need to subtract that to bring it back to the original one. And then for the other one, I can do the exact same thing. You get the idea. So for this one, I'm going to substitute this. Minus, I have first derivative of that one, first derivative of this one. So I can substitute those. And if I substitute it, what's interesting is these terms will then subtract to become 0. So I'll end up with this. I'll have T0, then it will be dx minus t dx. I'll have okay. Let's just write down the right side. Have here Okay. So now what I'll do is I'll take out the differential as a common factor. I can take a t as a common factor as well. So I'll end up with something like this. So we'll have the first derivative of sub k is n minus, then I'll have first derivative n k there. So okay, oh, this is supposed to be okay, sorry. Right, I can integrate on both sides over the total range of the x, which is 0 to L. So then I'll end up with this. If I integrate this b, so the whole range, and here I'll have lambda. Okay, integrated over the whole range. Right. If we look at the left side now, we can actually substitute the boundary conditions. Now at 0, we don't really care about the 0, 1. We know that these is 0 at 0. So that term will just disappear. So we'll end up with this. We'll end up with, if we substitute for k, we'll end up with, it's going to be a, it's actually this minus k. So it was that times, then it's going to end up being n. We'll have minus t0. Substituted that now. K 0. This is going to be n k. And on the left side, I'll just have one. Okay. Now, if I multiply the t inside, I'll end up with a minus k, and you'll end up with a plus k. And we can see that the left side actually will subtract to become 0. And so, thus, I've shown that this is actually equal to 0. And we know that this is not 0 since it's two distinct eigenvalues. So it means that this part must be 0, but that shows that if I multiply two different eigenfunctions and I take the integral with respect to my density, mass density, then I get 0. So that shows that my eigenfunctions are orthogonal with respect to the weight function, which is the mass density function. So I've now answered that question, and that will help me to actually solve my solution, or my coefficients rather, which, so I have this. Okay, so now I can calculate my coefficients by taking the Fourier transform of both sides, but with respect to my weight function. Well, after I've obviously substituted t equals 0. So if I sub t equals 0, I'll end up with this. So we know that the initial position was fx, and so I'll end up with this. So this is what fx will be equals to. So to calculate the coefficients, I'm taking the Fourier transform on both sides with respect to the weight function. So I'll end up with this, and I'm going to integrate it over the whole range. Sorry, I have to take it with respect to the weight function. Okay. So this, and then on this side, I have an, which can be side. Oh, sorry, again, respect to the weight function. Okay. Now, thus, I'll have an equals, oh, excuse me. Okay. I'll have an equals okay, so I've just taken the Fourier transform on both sides, and with respect to my weight function, because I know it's my eigenfunctions are orthogonal with respect to the weight function, which is the density, the mass density. And that is how I got to n. So my solution is then there, as you can see there at the top is my solution, with my coefficients being equal to this. So we've solved the differential. We've showed what the coefficients are equal to, taking the Fourier transform on both sides. Before we could take the Fourier transform, we had to know what the weight function is, which we've shown as well. So we've shown to what weight function are they actually orthogonal. And then we've also actually shown the differential equation and boundary conditions that is satisfied by my eigenfunctions. And so we've covered all the questions that were asked. And that, in fact, is then the solution to our problem. I hope that helps. If you have any questions, please leave a comment, like and subscribe first, of course. If you have any questions you'd like me to take a look at, please leave it in the comments below as well. And thank you so much. I see you guys in the next video. Bye-bye.